This is section 4.2 and 4.4, solving systems with substitution and applications. So when graphing is not feasible, or you just don't feel like graphing, there are two other methods for finding solutions to a system of two linear equations. Each solution has an x and a y value, like we saw last class. So we will find the solution to both variables, but only one at a time. So we're going to solve for x and then get y, or solve for y and then get x. The first method we're going to learn is called substitution. And what we're going to do is substitute, or replace, one variable for an equivalent expression in order to combine the two equations and solve for one of the variables. So if you think of substitution, it's kind of like a replacement. If you remember substitute teachers when you were in high school, or in basketball when they sub out one player for a different player, if someone gets injured they have a substitute player or a replacement player. It's that same idea. So the steps for this, we're going to talk about each step, and then I'm going to go through an example as we learn each step to help you see what the step looks like. The first step is to isolate one of the variables and one of the equations. So in this example we have 2x plus y equals 10. That equation's in standard form. And we have x equals y plus 2. If you notice in the second equation, the x variable has been isolated. So that's what I mean when I say isolate one of the variables. It should say x equals an expression or y equals an expression. It doesn't matter which one, as long as one of the variables is isolated in one of the equations. The next step is to make the substitution to combine the equations. And this part looks a little confusing at first. If you have a different color, it can be very helpful. It's best to put parentheses around the other side of the equation. So you have your isolated variable, your equal sign. Whatever is after the equal sign, if you put all of it in parentheses in a different color, it can really help you see it. Then we're going to look at the first equation, and we're going to replace the variable x with what we call the equivalent expression. So I'm going to take this x out of the first equation, and we're going to replace it with y plus 2. So I'm going to use two different colors now to write the equation. So I'm going to be rewriting the first equation, replacing the x with what it's equivalent to. So the 2 in the first equation is still going to be there. Instead of the letter x, we're going to replace it with y plus 2 in parentheses. Then the plus y and the equals 10 are all still there. So we put the two equations together using that method called substitution. So what we've done is eliminated one of the variables, and now we can just solve for y. So step 3 is to solve for the variable. So you might have an equation with all x's, or you might have an equation with all y's, and you solve for whichever variable is in that equation. So we have 2 times y plus 2 plus y equals 10. And we're going to use our solving skills from chapter 2. We'll distribute. We have 2y plus 4 plus y equals 10. Then we'll combine like terms. We have 2y plus 1y. That gives us 3y. And then plus 4 equals 10. Make sure you can see what I'm doing. So we combine like terms, and then we'll solve for y. We'll go ahead and subtract 4. That's 3y equals 6, and divide by 3, and we should get down to y equals 2. That's one of our answers. Feels like you're done because we've already done so much work, but that's one of the answers, and we need two answers for these. Remember, we're going to have an x and a y value in each solution. So we just figured out that y equals 2. Once you've done that, your next step is to plug in the solution into either of the original equations. So we'll go back to the very top to the original printed equations, and then we can solve for the other variable. And so it can be either one, it's your choice. You want to pick the one that looks easier. So we figured out what y equals. If we plug it into the first equation, we can solve for x there, or we can take the second equation and solve for x there. If you look at the two equations, the second one's a little simpler. We have x equals y plus 2. So it's your choice, but pick the one that looks easier to you. We're going to take that answer and plug it in for y. So x equals 2 plus 2, which is 4. So now you have your answer for x. There's a lot of work, it gets a little messy, and you're always going to have two answers, and they usually end up kind of all over your paper. So once you have your two answers, you're done. The last step is to write your answer. So it says state your solution as an ordered pair. So remember, this solution is where two lines cross. It's a point where two lines cross. Remember, we always put x first and then y. So the way we would write this answer is 4, 2. The x answer goes first and then the y answer. So those are your steps for substitution. Again, isolate one of the variables. Make the substitution, which is kind of confusing at first, but you'll get used to that. Different colors can help you there so you can see your substitution. Solve for the variable you have. Should be pretty straightforward solving. Once you have one answer, go back to the original set of equations, pick one of the two equations, plug in that solution to get the other variable. Then once you have your two answers, you state the final answer as an ordered pair x, y. So let's turn to page 5. Pause the video and try example 2 on your own following those same steps. Pause the video and try example 2. Alright, in example 2 we need to find an isolated variable. We either need to isolate it or pick the equation that has the isolated variable. You notice here x is isolated, so x equals y plus 1. I like to put that part in parentheses so I don't get it mixed up. Now I'm going to make the substitution, so the 2 from the original equation is still there. Then I'm going to replace x, or substitute x, with y plus 1. Then minus y equals 9. So it's like you're combining the two equations using that substitution method. Then you distribute your 2, so you have 2y plus 2 minus y equals 9. And we're using our solving skills. From here, we'll combine like terms. 2y minus y, if you want to put that 1, that can help you so you can see it. That's just going to give you y, 1y, plus 2 equals 9. So then we subtract 2, and y equals 7. That's one answer. We're only a little over halfway done, but that's only half of your answer. Now we're going to take that answer and plug it back into one of the original equations, whichever one looks easier. I'm going to say the bottom one looks easier. So x equals y plus 1. I just figured out y is 7, and 7 plus 1 means that x equals 8. So our solution is going to be 8, 7. So it doesn't matter which order you solve them in, for x first or y first, it doesn't matter. When we write our solution, x always goes first and y always goes second, just like in chapter 3. If you'd like to, you can pause the video and try examples 3 and 4. If not, you can just follow along with me. In example 3, you'll notice that the y variable is isolated, y equals 3x. Again, I like to put that in parentheses. Now I'm going to replace the y in the original equation with 3x. So we have 5x, the minus sign is still there, and then you can put parentheses just out of good habit, equals negative 2. Watch your signs very carefully here. So it's going to become 5x minus 3x equals negative 2. Then I'll go ahead and solve for x. 5x minus 3x is 2x equals negative 2. Divide by 2. So x equals negative 1. That's one answer. I'm going to plug that back into either one of the original equations. The second one looks easier. So y equals 3 times negative 1, which means y equals negative 3. So what we're doing is, instead of graphing, we're solving these algebraically. If we were to graph these two lines, which we could, this is where they would cross. They would cross at your solution, negative 1, negative 3. Remember, x goes first, then y. Example 4 is very similar. The y variable is already isolated. So I'm going to put parentheses around what it's equivalent to. I'm going to take that y out of the first equation and substitute in 2x. So we have 7x minus 2x equals negative 15. 7x minus 2x is 5x equals negative 15, and then divide by 5. So x equals negative 3. That's one answer. Now we're going to use that to get our second answer. I'm going to plug into the second equation again because it looks easier. Y equals 2 times x, which is negative 3. So y equals negative 6. And then we write our solution as an ordered pair, negative 3, negative 6. So there's a lot of these to practice on your homework. There's also extra practice in my math lab if you want to print a page of extra practice for substitution. And let's move on to page 6 with some more examples. You can always pause the video or go back and watch it again. You can also try each problem and then play back the video to see how you did. Example 5 is a little bit different. It takes a little bit more work. So if you notice, we have 7x minus 3y equals negative 14. None of the variables are isolated. Then we have negative 3x plus y equals 6. Also in standard form, none of the variables are isolated. But if we look at all the coefficients, the easiest one to isolate or to get by itself would be this y variable. I can isolate that pretty easily by just adding 3x to both sides. So sometimes it takes a little bit of work to isolate one of the variables. It should be a simple step, just moving one term to the other side by adding or subtracting to get one of the variables isolated. If that doesn't work, I'll show you a different technique in the next video, but right now it should only take one thing, one move, to isolate one of the variables, or it should already be isolated for you. So I took that one step. The y variable is isolated. It's equivalent to 3x plus 6. I'm going to replace the y value in the first equation with that equivalent expression. So I have 7x minus 3 instead of y. I'm going to put 3x plus 6 equals negative 14. Then I'm going to distribute that negative 3, just using our solving skills. Equals negative 14, so that's going to be negative 2x minus 18 equals negative 14. Add 18 to both sides. You should be really good at this part by now. Divide by negative 2. And I got x equals negative 2. Took a little bit more work there, but it should be simple solving steps that we learned in chapter 2. Now that I've got one answer, I'm going to plug back in. I always suggest one of the originals. If you've moved a term over nice and simple, then you can go ahead and use the new one. But you can also play it safe and plug it into one of the originals. So either way will work. If I plug it into the second original equation, replace x with negative 2. That gives me positive 6 plus y equals 6. And if I subtract 6 from both sides, I get y equals 0. If you plug it into this new equation, you should get 0. If you plug it into the top equation, you should get 0. Students are very afraid of the answer 0, but it's okay. It happens sometimes. Our solution would be -2, 0. Nothing wrong with 0 as an answer as long as you've done it mathematically correctly. Go ahead and try example 6. Pause the video and try it. Then you can play it back. Again, on example 6, both equations are in standard form, so none of the variables are isolated. The first equation, those coefficients are big, so it would take a lot of work to get one of them isolated, but on the second equation, this y term is already almost isolated. So all we have to do is move that 2x to the other side, and we get y equals 2x plus 8, and we can make our substitution. So I'm going to change colors here. So y equals 2x plus 8. So I'm going to plug that into the y in the first equation. 5x plus 3 times 2x plus 8 equals -9. Distribute the 3. So the 3 times 2x will be 6x, 3 times 8 is 24. Combine like terms, that's 11x plus 24 equals -9. Then we'll subtract 24. 11x equals -9 minus 24 is going to give you -33. And divide by 11, and x equals -3. You should usually get integers, positive and negative integers as answers. Very rarely do we get fractions or decimals because that just makes our job 10 times harder to plug back in. So when you're solving, you should get an integer, 0, a negative, or a positive. If you get fractions or decimals, you might be doing something wrong. Just always double check your work. So now that we have x equals -3, we can plug it back into one of the original equations. So -2 times -3 plus y equals 8. I just always take the one with smaller coefficients. So that's 6 plus y equals 8. Subtract 6. Y equals 2. So my solution would be -3, 2. So it's important to put the answers in the correct order, x and then y. Alright, let's look at example 7 here. Looks like the y variable is already isolated in the second expression, so I'm going to make my substitution there. I'm going to take that y out and replace it with that expression. So we have 2x plus parentheses -2x plus 1, just to be technically correct. You would distribute if there was something to distribute, but all that's going to do is make it -2x plus 1 equals 0. 2x minus 2x is 0x plus 1 equals 0. 0x is just nothing. You get down to 1 equals 0. So in this one, the variables disappeared. Even if you would have substituted the other way, the variables would have disappeared. So no matter which way you solve this, you should get down to something where the variables disappear. And what you get does not make sense. One does not equal 0. That does not make sense. So this is a case where you have no solution. So instead of having a value for x and a value for y, you have no solution because you get down to an equation that does not make sense. And in a minute, we're going to go back to page 2 and fill in that last row of our chart. We'll do that here in just a second. Remember, most of the time we get one solution. Every now and then we get no solutions, and then sometimes we get infinite solutions. We'll talk about that more here in just a minute. So on example 7, you did everything mathematically correctly, you made your substitution, the variables disappeared, and you get down to something that does not make sense. There's no solution. Go ahead and try example 8. Pause the video and try example 8, and then we'll go over it. So on example 8, The first equation's in standard form, sort of, kind of out of order, but the x and the y are on the same side, so it's not isolated. The second equation is just kind of funky, but if you look at the coefficient on x and the coefficient on y, neither of them are easily isolated. So I'm going to go up here and I'm going to subtract 2x from both sides, and that's going to give me y equals negative 2x plus 3. And that's the substitution I'm going to use in the second expression, or the second equation. So from there, I'm going to take negative 2x plus 3, I'm going to plug it in where I see y in the second equation. So we have 4x equals 2 minus 2 times negative 2x plus 3, making that substitution. Distributing. So you get 4x equals 2, then you're going to have negative 2 times negative 2x, which is positive 4x, and negative 2 times positive 3, which is negative 6. If we combine like terms, we're going to put the positive 2 with the negative 6. We should get 4x equals 4x minus 4. And then when we go to solve that, we would subtract 4x. Again, that's going to give us 0 x's equals negative 4, which is just 0 equals negative 4. So even though we did everything mathematically correctly, the variables disappeared. And we get to something that does not make sense. If the variables disappear and you get to something that does not make sense, there is no solution. Let's look at the next one. Example 9. Looks like the y variable in the second expression is already isolated. So I'm going to make that substitution, put parentheses around that and make that substitution. So I have 9x minus 3. Instead of y, I'm going to put negative 6 plus 3x equals 18. So 9x, this is going to be plus 18 minus 9x equals 18. When we go to combine like terms, we have 9x minus 9x, which cancels out, and we get down to 18 equals 18. Here again, the variables disappear, but we get down to something that's always true. 18 equals 18. That is always true. So up here we got down to something that does not make sense. Here we got down to something that's always true. If it's always true, you have infinite solutions. Every ordered pair that works for one equation is going to work for the other equation. Infinite solutions. That's on our chart. When we have the same line twice, like we talked about in class, you have infinite solutions. They are completely overlapping lines. Go ahead and pause the video and try example 10. And then we're going to go back and fill in the rest of the chart on page 2. So on example 10, again, you've got an equation in standard form. And you have an equation with just a term on each side. Kind of funky. A couple things you can do here. You could divide the second equation by 2 to isolate one of the variables. Or you can move the 3x. I think most of you probably moved the 3x. So you're going to get y equals negative 3x. Now we can make the substitution. So we're going to take that 3x and we're going to plug it in where we see y on the second equation. We have 2 times negative 3x equals negative 6x. 2 times negative 3x is negative 6x. And again, you get something that's always true. Here the variables don't disappear, but you still see the same thing on both sides. So no matter what x value I pick, that's always going to be true. So the variables might not necessarily disappear on these, but you get down to something that's always true. If it's always true, you have infinite solutions. So we just went through 10 examples. Most of those 10 have a nice XY solution. Nice XY solution, XY solution, XY solution. Every now and then you get a no solution. That shouldn't happen very often. And every now and then you get infinite solutions. That should also not happen very often. So let's go back to page 2 of our notes and fill in the rest of our chart. I know the rest of mine's not filled in. I had to print a new one from home. But if we think about this algebraically, if we have one nice XY solution, one point where they cross, algebraically we're going to get down to x equals some number and y equals some number. Nice, pretty two answers. If we have no solutions, we're going to get down to something like 0 equals 1. Something that does not make sense. That's what it looks like algebraically when you have no solution. Something that does not make sense. When you have infinite solutions, you get down to something that always makes sense, like 5 equals 5. Something that's always true. If it's always true, that's when you have infinite solutions. So again, most of the time you're going to solve it algebraically. You're going to get x equals some number, y equals some number. Every now and then the variables will cancel out and you get down to something that doesn't make sense, like 0 equals 1, and you have no solution. This is no solution. And then every now and then the variables may or may not cancel out, but you get down to something identical on both sides that's always true, and that's when you have infinite solutions. So those are the 3 ways to algebraically get your answer using the substitution method or the next method we're going to talk about in the next couple videos.